Knuth-Morris-Pratt algorithm is an efficient string matching algorithm. String matching is to check if a pattern string exists in the text. The naive approach involves sliding the pattern over the text and checking for matches character by character. Verifying each start index takes at most m comparisons, and there are n indexes in total. So time complexity of this naive approach is OM times n. Knuth-Morris-Pratt algorithm, however, can do string matching with time complexity of OM plus n. The optimization comes from an important observation. When we encounter a mismatch, instead of starting over, we can use the information from the matched part before this mismatch. If the first k letters are the same as the last k letters, we can skip ahead. This means for the next match, we align the pattern with the second occurrence of these k letters. In this example, the first and last two letters in the matched part are both AA, and we align the first AA in the pattern string with the second AA in the text string. We can understand this as we don't need to process the same substring twice. The above scenario can be generalized as what's called longest prefix-suffix, which is the longest proper prefix of a string that's also a suffix. Proper prefix here means not including the whole string itself. We'll simply call this as LPS for the rest of this video. Let's look at some examples. In the first example, we have AA at the beginning and end, so LPS is AA. In the second example, it may look like LPS is AB, but if we check the definition again, the LPS is just single letter A. In the third example, LPS is AAB. The fourth example demonstrates a case that prefix and suffix can overlap. In the last example, the LPS is just empty string, because the only non-empty prefix is letter A itself, which is not a proper prefix. KMP algorithm uses the length of LPS at each ending position of the pattern string. This information is stored in an array called the LPS length table, which has the same length as the pattern. The J's element in the table stores the LPS length of the first J letters in the pattern string. Let's take an example of what this table looks like. Notice that here we're focusing on the definition. How to efficiently construct it will be covered in later. Now, let's look at the code together with an example. We define two pointers, I for text string and J for pattern string. Also, we have the LPS length array, but we ignore how it's constructed for now. If text I and pattern J matches, we simply increase both pointers by 1, so that in next iteration we compare the next character. When there's a mismatch, if J is greater than 0, which means there's a matched part before this mismatch, then we backtrace using the LPS of the matched part. Notice that line 12 points J to the next character of LPS, and in the next iteration the character at this index is being compared. On the other hand, if J already points at the beginning of the pattern string, we can only try the next start position. Here, the LPS length of the first 5 letters is 2, so we update J to 2. Also, here we effectively change the start position in text string from 0 to 3. Here we got another mismatch. We do the same. LPS length at index 2 is 1, setting J to 1. Another mismatch. The LPS length at index 1 is 0, setting J to 0. Still another mismatch. This time J is already 0, we increase I by 1 instead. Let's analyze the time and space complexity, and we'll ignore building LPS length table for now. For time complexity, we need to figure out how many times the while loop can run. The key observation is that the pointer I for the text never decreases. So the I increases at most n times. The pointer j for the pattern only increases with I, so it also increases at most n times. Another key observation is j can decrease only when j is greater than 0, so j can decrease at most n times. As a result, the while loop runs at most 2n times, giving a time complexity of on. For space complexity, the algorithm requires om space to store the LPS length array. Finally, we'll look at how to efficiently construct the LPS length table. Again, we first quickly go through the brute force approach. There's 2 nested loops. The outer loop iterates through all ending positions in pattern string for calculating LPS length I. The inner loop iterates through all possible LPS length, and then verify if prefix and suffix are equal. Notice that time complexity for substring comparison is om. So time complexity is om cubed. To optimize the time complexity, we can use the prior result for j-1 when processing current position j. There are 2 optimizations to do. First, we can try to extend the LPS at j-1. If next string matches with pattern j, then we just add 1 to previous LPS length. Now, what if the current character can't extend the previous LPS? This is what the second optimization is for. As the longest prefix-suffix won't work, we'll want to try extend second longest prefix-suffix, and then third until there is no longer a prefix-suffix. Like in this example, A is also a valid prefix-suffix. But how do we find the second longest one? Now we'll use one important observation. Because the blue string and orange string are same. Checking first K letters in blue string equals last K letters in orange string is equivalent of checking first K letters in blue string equals last K letters in blue string. This is exactly same as finding LPS for blue string, the previous LPS. So in this example, the second longest prefix suffix is the LPS of ABCA, which is A. And third longest prefix suffix is the LPS of A, which is empty string. Summarizing above 2 optimizations, we have this code. This is very similar to the string match code. We define one pointer j for current position, and one pointer len for tracking the next LPS length we'll try to extend. This variable is needed because we can repetitively take LPS multiple times. In each iteration of while loop, line 7 to line 10 handles the case when the current position is able to extend the previous LPS. Line 11 to line 18 handles the case when it's not. If there's a mismatch and len is greater than 0, we try to extend a shorter prefix suffix. If len becomes 0, meaning the first character in the pattern string is different from position j, then we're sure the LPS at position j is empty. Also notice that the LPS length of the first character is set to 0 at array initialization instead of in the while loop. Now let's run with the example. With the 2 optimizations, the LPS length table can be built with linear time. Similar to how we analyze the string match code, the while loop runs at most 2m times, giving a time complexity of om. So, overall time complexity for KMP algorithm is om plus n. For space complexity, OM space is required to store the LPS length table. And overall space complexity is OM. Besides the string match code we mentioned earlier, actually it's possible to do string matching using the build LPS length function alone. First, we construct a concatenated string, pattern string at beginning, then a separator character, and text string at the end. The separator character can be any character not in text and pattern. Here we use hashtag as an example. Then we run build LPS length function on this concatenated string. If the result includes an item with value M, then we found a match. But one thing to notice is that the space complexity of this implementation increases to OM plus N, as the LPS length table now has the same size as the concatenated string.